Yeah, it's Roberto. Yeah, and Juan. All right.
Thanks for joining us today, guys.
We're going to put it on data.
Thanks
for that.
Good to start. And apologies for the technical delays. Today we've got Roberto presenting his master on 3, final hurrah. Well, sure, it'll be a great PhD, but it's a great PhD. On computational modeling, compaction bands and geomaterials. Take it away, Roberto.
Thanks, Hugo, for the introduction. So today I'm going to present my findings around my project during this PhD that is related to the phenomenon of compaction bands.
One thing I've got is this one. I know you're a Warburg, so
All right.
online still here.
This is working. Okay, great. Let's start talking about what is compaction bands for us. So compaction bands are a type of deformation bands that are narrow planar zones that appears mostly in porous rocks, where we've got a different set of features from the matrix. We've got areas with high density, low permeability, high mineralization processes, and or low porosity, or everything happening at the same time, or manifesting in different ways. Related to this phenomenon, we've got a lot of experimental evidence and also geological evidence in outcrops, like this outcrop here in Utah, in the US. And something that the researchers realized is that this phenomenon appears in a set of patterns that represent some periodicity and some thickness to the centimeter scale. So we can see here an image of a CT scan in a porous rock that presents a compaction band. And we can see that we've got a well-defined region of low porosity inside the band. So there are plenty of theories that try to explain this phenomenon. One of the most recent ones, is this theory from Manolis Vediakis and Klaus Regenauer, that it's basically an approach different from the previous approaches in this type of phenomenon. They were trying to link a traveling wave problem with the onset of these compaction bands. So basically they made a comparison between a variable that it's a stress manifestation with the way a wave propagates in a medium. So at the end, they ended up formulating an adimensional equation, a nonlinear equation that explains the periodicity and the thickness for the compaction bands. The concepts behind, in a nutshell, would be that they are trying to solve a nonlinear diffusion equation where you've got an overstress measure that is represented by this U, and then this nonlinear term is a term that appears from the contribution that is going to be given by the viscoplastic strain rate acting in the mass balance equation. So at the end, they did a dimensionalization of the equation, and they ended up having this one. And then this term here, it's showing, or it's related to some chemical process here. But it could be any other multiphysical process. That's one of the main outcomes of the framework, that it was not only focused on the mechanics, but in the multiphysics in general. So what's the issue with this equation? This equation was highly nonlinear, and we need to build a robust enough numerical framework to solve it. When we tried working with standard finite elements, we realized that we started to have a spurious solution, given that we have initial guesses or stress states that were far from the condition I want to reach. So at the end, we decided to use an adaptive stabilized finite element framework that was developed by Victor Callo and their collaborators in 2020. This method inherits all the stability properties from these continuous Galerkin methods. It allows us to have an enrichment in the test space functions, so I can have different polynomial degrees without losing any of these properties. I can use iterative solvers related to it because I've got a saddle point formulation at the end, and I've got a stable solution, and then I've got a residual representative, which is a variable that helps me to guide adaptivity on the fly. So I can do both things at the same time. The original idea was thought for only linear problems, and it was explained for advection problems. So the first part of the project was focused on expanding this to diffusion problems in any way, so heterogeneities or anisotropies. And then we dealt with nonlinear problems, trying to look for different branches in the nonlinear problem. And then we did the proper extension for the noidal equation that explains this phenomenon of compaction bending. So at the end, we ended up building a framework where we can deal with problems with diffusion, where we could have some singularities that require to have a well-guided adaptive scheme in order to find enough resolution to solve these points in our meshes. So, for example, this is a clear example where the method shows that it's powerful enough to do it. Then we attack nonlinear problems when we were able not only to solve the problem nonlinearly, but also to find both branches of this Ratu equation, which is an equation that has a similar structure of the conoidal one. So given that we ended up building a robust enough framework, we decided to tackle the problem of the conoidal equation. So we ended up making a series of tests where we were dealing with the problem. And we can see that if we start with the initial guess in blue, and we use only standard FEM, even if I use a fine enough mesh, I am going to have some spurious oscillations in my solution. I cannot reach the right solution. I just have noise. So when I use the adaptive finite element method, I am able to guide the mesh through the nonlinear process and find the right solution. So we did, why this works, it not only is working because of the way we are solving the problem with the adaptive stabilized finite element, but also for the way we are controlling convergence in our method. So we're using a damping scheme based on works of Bank and Rose for global approximate methods, where we can bring points that are far enough from our typical region of the slope when we are solving a nonlinear problem with Newton methods. If I have control over the size of the step, I ended up having a more robust method to bring solutions from a wide range of initial guesses. So we ended up doing that. We published that paper in 2021, where we were showing that for a wide range of initial guesses, we can ended up finding the right solution for our problem. the equation, as I show, has some parameters inside the formulation that depends on how different quantities are acting in the phenomenon. So we were able to tackle this for a wide range of parameters. And then after that, we state that we were able now to solve the equation using a more realistic set of conditions. So we changed from Dirichlet boundary conditions to periodic conditions. And then we could start with an initial perturbation of our stress state, and we ended up retrieving different types of solutions. So we can retrieve the classical homogeneous deformation pattern. We can retrieve two peaks localization, which means I've got a set of two bands, or I could retrieve even a richer solution of bands. So all the idea was supported by this adaptive scheme. So later we made some comparisons because we wanted to see the power of the method for not only a dimensional equation, but also for 2D equations. So we ended up solving an extension of the set of the conoidal equations for cracking in viscoplastic solids. And we can see that we can obtain patterns also in solids like when the clay shrinks in a surface. So all this first part of my project, it was focused on trying to build a numerical framework for a phenomenological explanation of what we were seeing in the compaction boundary. However, we didn't deal with the mechanical part of it. We then realized we wanted to try to explain from basic concepts in solid mechanics what was happening for the bands to occur in the material. So we ended up building a failure criterion, taking some ideas from the previous work of the conoidal equation. So we wanted to work with viscoplasticity. We wanted to see rate dependency. So we had to work with a viscoplastic approach, but we wanted to do it correctly. So we used a consistent one. We spent our efforts on building one of the first consistent viscoplastic approaches. So what is happening? If we see all the types of deformation bands in a PQ space, basically isotropic and deviatoric stresses, you can travel, or you see how the evolution goes from pure dilation states until shear enhanced compaction bands, pure compaction bands, and once you are close to the isotropic state, you start to have something called diffuse compaction. This concept wasn't clear enough in the literature, so we tried to build some indicator to understand what's going on here. And for that, we used a viscoplastic approach consistently. So we picked basically a CAM-clay model where we plug all the Persina's overstress concepts, and then we ended up building this superloading current cap that has the Cier surface, the classical Cier surface, plus or minus the contribution of the viscoplastic multiplier and some overstress parameter that depends on the way of the yield function. Well related to Persina's. So But for doing this properly, we needed to do it consistently. Most of the work in the literature was related to working with viscoplasticity in the way of persinas, but without any consistency. They weren't imposing the constraint. At the end, they were trying to solve this just directly in the algorithm, not from the beginning. So we tried to do it consistently, so we impose consistency in our new superloading surface. And we ended up having or relating, given that we were in critical state working with modified clay, that we could, from consistency, build an equation for the viscoplastic multiplier in the way of an ODE. So solving the ODE analytically, I could reconstruct the viscoplastic constitutive tensor, which allows me then to make a better analysis of what's happening when the localization appears. So we were able to reconstruct the viscoplastic constitutive tensor and to express the flux tensor in a stress invariant way using modified clay. We can see that the viscoplastic constitutive tensor is recovering the elastic one when it's at zero, and the elastoplastic one when it's reaching infinite, which makes sense for the framework of the theory. Now, in terms of bifurcation or localization indicators, the classical ones are related all to the acoustic tensor, which is basically a way to express the orientation of the localization plane. And we solved this eigenvalue problem in order to find what's going on with the orientation or the angle of this plane. This acoustic tensor concept is useful, but we realized it was incomplete. And that's sort of explained why all the literature was dealing with this diffuse compaction without being clear enough in the concept. So we had a necessary condition there coming from the classical concept of Cier, and we ended up building a new localization indicator. We call this the L tensor, where we found that this can help us to explain better the phenomenon for isotropic states, isotropic compression states. So at the end, this L shows the onset of the phenomenon when one of the eigenvalues becomes zero, and the direction is linked to the direction parallel to the eigenvector associated with the zero eigenvalue. So with this new framework, having the consistent viscoplastic approach and all this new concept of the L tensor, we decided to go through well-known stress paths in geomechanics. So we started with isotropic compression, and we realized that the determinant of Q, of the acoustic tensor, it wasn't vanishing at all when I was reaching infinite. Basically, it was staying here. It should go up to zero if I want to have a manifestation of the localization. So the concept wasn't complete enough. However, when we used L, we ended up having a matrix, a diagonal matrix, or a tensor with a diagonal matrix structure, where all the eigenvalues degrade up to zero at the same time. So that explains that in isotropic compressions, we are degrading in all the directions at the same time. And then the onset of the localization or the plane for the band is going to be associated to a new set of phenomena. We did the same for drain triaxial compression first for normally consolidated states, so what we call it like this. So we are starting from here, moving in this direction. So the flux tensor has a direction there, and then given that I'm doing a train triaxial compression, I know the direction of the principal stress. And then what we realize is that the onset of the localization appears or manifests itself when the component or the plastic flux is parallel to this principal stress direction. So when this happens, I've got compaction bands. And this happens also for the over-consolidated state. We can see here how we touch at 90 degrees, which is the angle of the plane we are measuring from the vertical. And immediately after, we've got a less pronounced, it stops being horizontal, it moves 10 degrees each side. But the concept is working. So finally, we wanted to try to link the concepts we were studying for the noidal theory with all this new mechanical approach. So we did a series of simulations just to close up like the general idea. So we ended up seeing that if we model a triaxial compression test, we were evolving from basically low confinement pressures to high confinement pressures in rocks. So at the end, we can see that for low confinement pressures, we're having shear banding, which is a phenomenon well known in the literature, and we were transitioning until compression or compaction bands. So this was based or built based on a viscoplastic approach. So we're using a viscoplastic model here. So this is validating all the things related to the mechanical approach. And at the end, we wanted to see what happened with the effective mean stress, that in some way it's the way we express this U variable we were tackling with the noidal theory. So at the end, we can see here in the picture that so we can define regions where our model is reproducing shear transitioning, shear enhanced convection, or pure compaction processes. Then if we see all the effective mean stress patterns, we can see that they are strongly correlated to the lab experiments. So there is a strong correlation between using a viscoplastic approach with all the noidal theory. At the end, using the stresses to explain how the bands are appearing, it's also valid. And it's something that it's supported by the simulations. So at the end, the main contributions are in two different fronts. We narrowed the gap within the general framework of the noidal equation applied to localization processes. We ended up building a robust enough numerical technique that it adapts itself and help us to solve nonlinear problems and find different branches of solutions. And from the theoretical part, we ended up proposing a new, consistent viscoplastic mechanical framework that allow us to enhance all the localization indicators through this L tensor. And at the end, all the simulations we did agree with the experiments under similar loading conditions, and it finds a physical correlation with the noidal theory from Bebiakis and Regen-Noweli. As future work, we propose that we could start exploring higher dimensional problems using explicitly this consistent viscoplastic approach. And one thing we are starting to work on is on using all this consistency in viscoplastic models for different types of localization, in this case, flow liquefaction for soils. That it's a hot topic right now. This is just a slide to show all the work produced during this period. We ended up publishing 3 papers. We've got 1 in review. Conference talks and visiting when we could go out. But yeah, it's been a productive time, I think. Thank you.
Thanks very much, Roberto. If there's any questions in the audience, I'll ask that you use this little thing so that people online can hear you. I'll pull up online in just a second. Any questions from the audience? All good? Bruce?
We can go back to the Viviakis and Reganalib equation there at the beginning. I think it's this. Yeah, that one there. Find u such that you have followed that equation. You use that equation.
I use that equation for the numerical framework at the beginning. Then there was something we were discussing some time ago that was building a framework plugging the mass balance with all the viscoplastic part. That's something that ended up being ginormous, for saying something.
Well, the reason I ask is I think that last term, mu, e to the beta mu u, involves kind of chemical reactions and fluid flow and stuff. So have you involved specifically fluid flow in what you've done as Viviakis did? The reason I ask is that they pointed to the fact that you not only could get compaction bands, you could get opening.
Yes, I can
solutions.
Yeah, we can produce dilation processes there. Too. Yeah. So I'm solving when the simulations at the end are more in the way of BIOS. So
yeah,
it's all in effective stresses. But it's not a couple problem.
And the other thing is that you showed a graph where with lambda, I guess lambda is that lambda there or is it their lambda? So they had the bifurcation setting in at lambda equals 13. I think.
Oh, this one?
Yes.
Yeah, that's their lambda.
It's their lambda.
Yes.
Okay. Would you agree with their number 13 or?
No.
Oh.
No, that's the first thing we realized, that you cannot say that the phenomenon is only conditioned by the diffusivity ratio. No, there are interplay of many more variables there. We started to see it with things like this. I don't need, so if I got 13, maybe I'm gonna go to a homogeneous deformation, but it's gonna depend on the stress states I impose at the beginning. So yeah, at the end, this make us think that we were tackling the problem in a wrong way too, because at the end, this is saying to you that you've got a spatial variable that is saying, so at the end, U is expression of overstress. I've got a region where this overstress is producing something in the mass balance, and at the end, it's reaccommodating itself. So it's not as straightforward as saying, now if I've got this value of diffusivity, like undrained conditions, I'm gonna promote the phenomenon with this set of bands. No, but that's something we ended up realizing later because we changed the conditions of the problem, putting it periodic. Because at the end, we wanted to tackle the periodicity.
So you must have a threshold for that lambda where you start to get localization.
Yes and no. Yes, if we are in a so if we what we could do is if we start from a well-known stress state, which is basically a chosen initial guess, I could state that I am gonna have some threshold for the lambda, which is what we did in the paper we published with this theory. But then, when we changed the conditions, we saw that it was not only related to the diffusivity, but also with the amount of overstress that was acting in that moment. This is close or wider, yeah. But I.
And then finally, you had an equation for lambda, the evolution of your lambda, with time. I think lambda dot equals.
Oh yeah, but that's another lambda. Yeah, maybe.
Yes, that's another lambda. I realize that.
Yeah.
But what was the solution?
The solution of this equation
Yes,
is this.
it's still lambda dot though.
Yes. So we are assuming that lambda dot start from a virgin stress state. So at the end, this is 0. But it's just for the sake of simplicity. We could state that we know this algorithmically.
Okay.
Yeah.
Thank you. That was excellent.
Thank you, Bruce. You were much help during the last part.
Any other questions? I've got one, Roberto. I'm not a computational geoscientist in any way, shape or form. But I do wonder, like, how do your new findings then impact, say, various stakeholders like the oil and gas industry or the maybe the minerals industry? How do they benefit from your work?
Sure. Thanks for your question because it's important. So there are basically two different areas. The first of them is mineral resources, maybe, because this process is also related to mineralization process. So in specific, if you've got the brittle ductile transition in the crust in the mantle, you can see that this pattern would manifest through some sort of consistency during the spacing. And so at the end, having a tool that could help you to predict what will happen, at least in the order of magnitude, allows you to make better mineral prospection, employ new technologies in a more efficient way, and so on. Another problem is related to the oil industry, because if this phenomenon happens, it's conditioning your fluid path. So given that it's going to be doing that, you would like to know under which conditions of stress, knowing some parameters of your rock, could this phenomenon appear. Basically, those are the two different or motivations or significance for the project.
Thanks, Roberto. Yeah, it was really helpful.
Thank you.
Yeah, Victor.
Just let me add to that if you have a new theoretical description of a physical process, that also allows you to go and reinterpret your data. So that's what you were saying. Like, if you have this spacing, you can interpret your spacing as a way of inferring the physical processes that happen when this happens. And also, it gives you new ways of imaging. So having this new way of understanding failure can allow you to develop new sensors, because new failure mechanisms can trigger processes that you can go and try to sense. So it's useful not only as a way of explaining processes, but also as a way of getting insight in the process that you up to now you were not able to explain. I'm not sure if it makes sense.
No, that makes no sense. So no, I don't understand the computational side of things, but I understand the applications.
Yep.
So if there's no further questions, I don't think there's any online. Please help me thank Roberto again for an excellent talk. And best of luck on the final part of the PhD.
Yeah. Thank you.
Sort of technical.